Green's theorem in the xy plane for this integral where C is closed curve of the region bounded by y equal to x and y equal to x square, the line and the parabola, right? So let's take R to be the region enclosed by the curve C, and since we are having here xy plus y square and x square, both these are continuously differentiable functions. So we need to apply here the Green's theorem. Xy plus y square and x square. These are the continuously differentiable functions in the region R, which we have taken. So therefore, by Green's theorem, the given integral, that is xy plus y square dx plus x square dy, is equal to the double integral over the region R. Okay, now because this is with dx, so we take this to be as p, and x square is with dy, so taking this to be as q. And the formula is, writing here, q is with dy, so we write curl q divided by curl x minus curl p divided by curl y. How to remember? If q is with dy, writing curl q by curl x. If p is with dx, we write curl p by curl y with negative sign, right? This is just the way to remember the formula, and this is dx dy. So now putting the value of q over here. So this is equal to the double integration over the region R. Curl q, what is q? It is x square. So this is curl of x square by curl x minus curl p by curl y. P is xy plus y square. So curl p, that is xy plus y square divided by curl y dx dy. So this is equal to the double integration. Okay, derivating x square with respect to x partially, we get 2x minus partially derivating this with respect to y, we get x plus 2y, right? Dx dy. So we get here 2x minus x to be as x minus 2y. So the integrand is x minus 2y. Now we need to put the limits for x and y. For that, first we just plot the curves and the parabola. For that, we just plot the given line, that is y equal to x, and the parabola y equal to x square. This is given to us. Let's plot this. The line y equal to x and the parabola y equal to x square, that is this one, intersecting the line at, let's say, the point A, and this is the origin. Okay, where this point will intersect, just put y equal to x in this. We get y equal to y square, and y square minus y equal to 0. From here we get y minus 1 equal to 0, that is y equal to 1. So when y equal to 1, from here x is also equal to 1. So this is the point 1, 1. Now for this region, the limits of x is from 0 to 1. So this is from 0 to 1. And the limits of y. Now for this region, if I consider any point, let's say here, what is the value of y at this point? At all these points, values of y is x square. And if I reach from this parabola to this line, what is the value of y on this line? It is y equal to x. So writing here x. So the limits of y becomes from x square to x. So this is equal to the double integration x minus 2y. Okay, what to write here? Because the limits of x are constant, we always have to write this on the outer integral. We always have to take the integral with respect to x as the outer integral because of the constant limits. And the limits of y is invariable. So we write here as the limits on the inner integral. So first we have to integrate this with respect to y. We get, this is xy minus 2y square divided by 2 and the limits x squared to x, and writing here dx. Let's cancel this. When putting the upper limit of y as x, we get x square minus x square, that is 0. Yes. So this is 0 minus. Putting the lower limit for y, we get this to be as x cube minus x to the power 4. And writing here dx. So this is x to the power 4 minus x cube dx. Integrating this with respect to x, we get x to the power 5 divided by 5 minus x to the power 4 divided by 4 with limits from 0 to 1. Putting the upper limit for x, we get 1 divided by 5 minus 1 divided by 4 minus putting the lower limit for x, we get 0 minus 0. So that is equal to 1 divided by 5 minus 1 divided by 4, which is equal to minus 1 divided by 20. That is, this right hand side is minus 1 by 20. To verify the Green's theorem, we also have to find the same answer for the left hand side. So let's evaluate this integral now. That is equal to the line integral over the curve C1 plus the line integral over the curve C2. For the curve C1, let's take this curve BC1 and this curve BC2. So this is your C1 and this is your C2 curve. For the curve C1, we need to put y equal to x square. Along the curve C1, we have y equal to x square. Right? So for the first integral, we have to replace y with x square. So we get x into, y is x square, so x into x square becomes x cube plus y is x square, so y square becomes x to the power 4 plus writing x square as it is, and dy becomes, because y is equal to x square, dy becomes 2x dx. So this is 2x dx. That becomes 2x cube dx. Is it fine? Okay. Let's move on to the second integrand. Okay, for the second integrand, we are having C2 to be y equal to x, right? So replacing y with x here. So x into y, that is x into x. This is x square plus y square becomes x square dx plus x square writing as it is, and dy becomes, because y is equal to x, so dy is dx. So writing here dx. And now writing the limits. Because the curve C1 is from origin to the point A, we have to integrate from origin to the point A. So the limits for the curve C1 is from 0 to 1 for x. And then we have to move back to the origin, right? From A to the origin. So the limits of x now becomes for the curve 2, that is from 1 to 0, opposite. So the lower limit becomes 1, upper is 0. Is it okay? Fine. This point is clear. Let's move further. X cube plus 2x cube is 3x cube plus x to the power 4 plus second integral from 1 to 0. It's x square, x square, x square. That is 3x square dx. Okay. Integrating this, so this is 3x to the power 4 divided by 4 plus x to the power 5 divided by 5, limits from 0 to 1. Plus integrating this is 3x cube divided by 3, limits from 1 to 0. Let's cancel this 3. Putting the upper limit for x, we get 3 divided by 4 plus 1 divided by 5. Minus putting the lower limit for x, it is 0. Plus putting the upper limit of x, it is 0. Minus putting the lower limit for x, it is 1. Taking the LCM, this is 20, this is 15, plus this is 4. Minus 1, right? So this is further equal to, 15 plus 4 is 19. This is 19 divided by 20 minus 1. That becomes minus 1 divided by 20. So this is the same as that of the right hand side integral, the double integral. So we have evaluated this line integral also to be minus 1 divided by 20. Hence the Green's theorem is verified. Let's write this. Let's mark this as 1 and marking this result to be as 2. So from 1 and 2 we get the double integral over the region for this integrand to be equal to minus 1 divided by 20, and this is also equal to the line integral of this integrand. Hence, the Green's theorem is verified. Okay, thank you. Stay blessed. Have a nice day.